Hi folks, welcome to chapter 10. This chapter is made up of solids, liquids and gases. But in the first part, we already looked at gases. So in this lecture, we are going to concentrate on the solids and the liquids. When we looked at chapter 1, we did see the states of matter. And we said the common states of matter were the solid, the liquid and the gases. So we said the solids have a definite shape and a definite volume. And what about the atomic molecular arrangements? We said the particles are close together and held in a fixed place. For the liquids have a definite volume and they adopt the shape of the container. How are the molecules or the atoms arranged? The particles are close together but they move freely past each other. For gases have no fixed shape and no fixed volume, so they adopt the shape of their container that define themselves and the volume. And how are the atoms arranged in gases? The particles are far apart and they have very little interactions. Now we are going to look at what is called phase changes. A phase change is a transition from one state of matter to another. So that basically we are going to be looking at the states when a solid may change to a liquid, or a liquid changing to a gas, or a gas changing to a liquid, and all of that. So here we have water. Here we have water in its three states: the solid, the liquid, and the gas. So the solid here is ice. As you see, the bear here, the polar bear, is standing on ice. So what happens is that if heat energy is supplied to the ice such that it overcomes the forces of interaction, the ice is going to melt into liquid water, like you see here. Now with this liquid water, if energy is still supplied to the liquid water, that it overcomes the forces of interaction between the water molecules, the water will change to a gas. So what is important is the change of state from solid to liquid is called melting, and the change of state from liquid to gas is called evaporation or vaporization. Now, when a gas changes to liquid, we call that process condensation, and when a liquid changes to a liquid changes to a solid, we call that freezing. So we also have the situation where a solid can change directly into a gas without passing through the liquid, and we call that phase change sublimation. Now, it is important to note that the forces between particles influence the physical properties. So the physical properties that you see for different substances, that are being influenced by the interactions that go on within that particle. So strong forces between particles will lead to higher melting and boiling points. So we are going to look at solids and liquids. So the solids, the shapes of the solids, the liquids that you see, the interactions between them gives the solids different properties. So we are going to be looking at the different types of solids and how the particles are arranged in the solids and liquids. So we are going to look at the first here, the ionic substances. As we already saw, we did ionic compounds. So here we are going to be looking at ionic substances. And a lattice is a rigid framework of atoms or molecules or ions. We saw that ionic substances are formed between cations and anions. So positively charged and negatively charged ions, and they attract each other so much such that the forces of attraction between them are very strong. And examples of ionic compounds here that we can see are sodium chloride, potassium chloride, magnesium chloride, calcium oxide, and aluminum oxide. So what is important to note here are the melting points. So you will see that the substances have relatively high melting points because of the way the attractions of the ions take place. So they are really strong that at times you need very high energy to be able to overcome the forces of attraction. So for it to melt, it needs a higher energy. So I want you to take note of these values. We are also going to look at metallic and covalent bonds. So let's look at the next form here, which is metallic substances. In metallic substances, they form lattices of tightly packed atoms. Like you see here, the atoms are tightly packed, and the electrons move easily between the atoms because the outer electrons have an attraction to the nucleus that is not so strong. So the electrons in the atoms can actually move freely within them. Now, the shapes of the metals are easily altered. The shapes are easily altered because the atoms can slide past each other. So how can they be altered? Through what we call malleability and ductility. When we talk of metals or the shapes being malleable, you can change them into different forms as you so wish. And when we talk of them being ductile, it means that it can be drawn into wires. Like you see the wires here, that is, they are being ductile. Now, for the metallic substances, when you have enough energy that you can overcome the interaction between the forces, you actually change them. For example, iron, copper, gold, aluminum, and lead, they can actually be molded into different forms here. So all you have to do is to supply enough energy to overcome the metallic bonds, and that will change the form of the substance. So here, if you look at the melting points, you see that they are lower than the melting point of the ionic substances, because here the particles are close to each other but not as close like the attractions that exist between the oppositely charged ions in the ionic substances. So the next type of substances that we are going to look at are the molecular substances. When we were looking at molecular compounds, we said molecular substances are formed between non-metals. So when we are talking about molecular substances here, we'll be looking at mainly non-metals. And we are going to look at two types of forces. The forces that exist within molecules, which are called covalent bonds. So these are the covalent bonds. We've seen the covalent bonds a couple of times. And we are also going to look at the forces between molecules, like you see here, and those are called intermolecular forces. So the forces within are called the covalent bonds, and the forces between are called the intermolecular forces. Now, we are going to come back later in the lecture to look deeply into the intermolecular forces. But before we get there, let's look at the other class of substances, which are covalent networks and polymers. For covalent networks and polymers, covalent networks are lattices of covalent bonds that form giant molecules. For example, we are going to be looking at carbon here. We are looking at two forms of carbon, which are diamond. You've heard of diamond, and it's important to note that diamond is carbon. It's a form of carbon. It's diamond and graphite here. Now let's look at the structures of the diamond and graphite. For diamond, the carbon atoms are bonded singly to three other carbon atoms. Each carbon atom is bonded to three others, forming a regular tetrahedron that extends in a very long way in the three-dimensional structure. That makes it to be very strong. That is why diamond is one of the strongest substances that exist. Now, looking at the graphite here, for the graphite, it has a trigonal planar structure where the atoms are arranged and they can slide past each other. So an example is the pencil that we used in writing is actually graphite. It's a form of carbon that is graphite. Now let's look at the covalent networks and the polymers in another dimension. So polymers contain long chains of covalently bonded atoms. So when you see wood here, Wood here is a polymer of a substance that we call cellulose. So cellulose is the monomer, and they combine together. So a polymer is formed from monomers. So monomers combine together to form long chains that are called polymers. And wood is an example of a polymer of cellulose. Another example is the polyvinyl chloride. Here, the pipes, they are made of polyvinyl chloride. We have polyethylene bags here. They are made of polyethylene monomers. So polyvinyl chloride, they are made up of vinyl chloride monomers that they combine together to form the polymers. So these are long chains of monomers. So here we can see how these are formed. These are the monomers here, and they are combined to form long chains to give what we know as the polymers. So let's have a summary of the solids and liquids before we get into intermolecular forces. As I've told you, we've said that we have basically 4 of them for the solids and the liquids. That we have the ionic substances, we have the metallic substances, we have the molecular substances, and we have the covalent networks and polymers. Now we are going to look at the molecular substances. We are going to go into details again to see the kind of forces that exist in these molecular substances. So the forces within and between molecules. We've already said that the forces within molecules are called covalent bonds, like we already saw, and the forces between molecules are called intermolecular forces. So here we have covalent bonds between this carbon and this nitrogen. We have covalent bonds, and between this molecule and this other molecule we have intermolecular forces. So what we are looking at here now, we want to look at the different types of intermolecular forces that exist in molecular compounds. So let's look at the first type of intermolecular force. The first type is the dipole-dipole interactions. We already saw how a dipole is formed in our previous chapters. So the next is a hydrogen bond. We go detailing into each of them, and the last is the dispersion forces. You can call them dispersion forces or London forces or London dispersion forces. So let's look at the dipole-dipole interactions. So the dipole-dipole interactions are attractions between polar covalent molecules. When we were looking at the molecules and how the polar bonds are formed, we said a bond is considered to be polar covalent when the electronegativity difference between the two atoms is between 0.5 and 2. So the chlorine here will be partially negative because it is more electronegative, and the hydrogen will be partially positive because it is less electronegative. Since chlorine is more electronegative, it pulls the bonding electron more to itself, and the hydrogen is left with just a small part of it. Now, this is what is going to happen. Since we know that this is the partial positive and the partial negative end, if we bring 2 of the molecules, we will see that the partial negative end here will be attracted to the partial positive end. So this forms a dipole. So this is where we have the dipole-dipole interaction. Same thing for this HCl. If you put them together, chlorine is more electronegative than hydrogen, and it will pull the electron cloud more to itself. And in a situation, this kind of scenario will still occur. That is why you see all of them being attracted to each other. Now, let's look at the situation here. We have 2 Erlenmeyer flasks here, and in this flask, we have substances that are dipoles. And in this other flask, we have substances that are not dipolar. Now, because of the dipoles that exist here, these substances, they are attracted to each other, which means that if you want to separate them, like if you want to boil them, you're going to need a higher temperature. But for these ones, because they are not held together by dipole forces, it's easier to evaporate them than these ones. So these ones for flask A, they will have a higher melting point and a higher boiling point than B. So let's look at examples here and explain some situations. We have the geometry here. We saw that carbon dioxide is a linear molecule. When we're looking at chapter 9, we said it's a linear molecule and it's not polar, because even though the carbon-oxygen bond is polar, there is symmetry here. The molecule is symmetrical. So the way the bond will be pulled in this direction is the same way it will be pulled in this direction, and that cancels out. So it has a zero dipole. Now, we also saw that sulfur dioxide, it has a bent shape and it has a small dipole. The small dipole will be in this direction. Now, for acetonitrile, acetonitrile is a linear molecule and it has a large dipole between carbon and nitrogen. Nitrogen is more electronegative than carbon, and the bonding and the electron cloud will be pulled more to the nitrogen. Now, there is something very interesting here that you will see. You will see that the boiling points come as a result of the interactions that go on within the molecule. So the boiling point of carbon dioxide here, it's minus 79 degrees Celsius. So this means that carbon dioxide sublimes, which means it transitions from the solid directly into gas at minus 79 degrees. Think about it, minus 79. So the structure affects the properties. Now, for sulfur dioxide will boil at a temperature of minus 10 degrees Celsius. Now, let's look at the acetonitrile. We've said acetonitrile has a large dipole. Because of its large dipole, it's interesting to note how the boiling point is very high. It has a boiling point of plus 82 degrees Celsius, and that is because of the structure. Now, let's look at the next type of intermolecular force here. We've already seen the dipole. The next one now is hydrogen bonding. So hydrogen bonding is a special type of dipole-dipole interaction where a hydrogen atom is bonded to a very strong electronegative atom such as fluorine, oxygen, or nitrogen. So there must be a hydrogen atom that is bonded to a very electronegative atom like fluorine, oxygen, and nitrogen. Now, let's look at the properties here, the boiling point, in relation to if there is a hydrogen bond or not. Now, let's look at the compounds that we have here. We have methane, we have hydrogen cyanide, and we have water. So, methane, it has no polar bonds, so it's covalent, and as such, there is no dipole. So it has, the dipole strength is 0. So if you calculate the formula mass, it's 16. Now for hydrogen cyanide has a dipole. If you calculate the electronegativity difference between nitrogen and carbon, you will have a dipole strength of 2.98. It's quite big, right? Now, if you calculate the electronegativity difference between oxygen and hydrogen, you will see that water is polar and it has a dipole strength of 1.85. Now, it is important to note here that even though the hydrogen cyanide has a higher value for the dipole strength than water, water is going to have some interesting properties. It will have a higher boiling point than hydrogen cyanide, and that is explained by the hydrogen bonds that exist in water. So let's see the boiling point. The boiling point for methane is going to be minus 162 degrees Celsius. So these numbers convey the relative size of each dipole, and you will see that the boiling point for hydrogen cyanide is plus 26 degrees Celsius. Interestingly, the boiling point of water is 100 degrees. Even though the dipole strength is higher than that of water, water has hydrogen bonds that exist between the molecules. So let's look at hydrogen bonding detailing. So hydrogen bonding is a strong intermolecular force between molecules containing hydrogen, fluorine, hydrogen bonded to oxygen or hydrogen bonded to nitrogen. Now, how does that come about? We know that there is a dipole that exists between hydrogen and fluorine, as we already saw in hydrogen fluoride. So because of that dipole, the electronegativity of fluorine pulls most of the electron density away, leaving the tiny hydrogen nucleus exposed. Now, because of this exposure of the hydrogen, another molecule that has hydrogen and fluorine as well, the fluorine section will be attracted to the hydrogen. That is exactly what happens here. So you see the fluorine here attracted to the nucleus here of hydrogen. So this forms what is called the hydrogen bond. Same thing here. So this allows other fluorine atoms to get unusually close, forming very strong intramolecular and interactions. So the conditions for hydrogen bonding is that a hydrogen atom must be bonded to an atom of fluorine, oxygen, or nitrogen. So that is the condition for hydrogen bonding. Now, as we've said, a hydrogen bond is a strong intermolecular force between the molecules containing hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen. So here is the condition for hydrogen bonding to take place. So here you see the hydrogen bonding between oxygen and hydrogen. The hydrogen here must be bonded to an electronegative atom of either fluorine, oxygen, or nitrogen, and there must be another atom of the fluorine. So there must be a donor and an acceptor for the hydrogen atom to form a hydrogen bond. So this is a covalent bond formed between hydrogen and oxygen in water, and this here is an hydrogen bond formed between water molecules. So hydrogen bonds explain the properties of water. Like you see here in water, we have the hydrogen bonds, the hydrogen attracted to the oxygen, the hydrogen attracted to oxygen. So these are the intermolecular forces here. Now, because of the strong intermolecular forces that exist, you actually see that this insect in picture A is capable of moving over water without sinking because of the strong hydrogen bonds that exist in water. So in picture B, you see the water molecules trying to form circles because there is that strong attraction between the water molecules, the hydrogen bonds. You see, they will always try to stick together. Now, that is the same thing here. The water molecules will try to stick together because of the hydrogen bonds that exist between the water molecules. So the last one that we are going to see for the molecular forces, we have seen the dispersion, we've seen the dipole, we've seen the hydrogen bonding. Now we'll look at the last one, which is the dispersion forces. So generally, all covalent molecules exhibit dispersion forces. So if you are asked which kind of forces exist in a molecule, in as much as you identify it to be a covalent molecule, there must be dispersion force. Now, if the forces are stronger, you then talk of dipole if there is a dipole, and if there is the hydrogen, you talk of that special type of dipole-dipole interaction where hydrogen is bonded to oxygen, fluorine, or nitrogen. So for the dispersion forces, there are weak intermolecular forces that result from instantaneous dipoles. So the dipoles are formed instantaneously. For example, we know that the hydrogen carbon bond is not polar. Okay, so there is going to be an instantaneous dipole that will form, and these molecules will be attracted to each other. I'm going to demonstrate to you how that instantaneous dipole forms and how they are being attracted to each other. Now, we know that the electrons in the molecule constantly fluctuates. The electron is not in one position, and as the electrons are fluctuating, they can move around and they become close, such that you see here, they can become close such that the partial negative is close to the partial positive, and there is going to be that attraction. So this is an induced dipole here because the partial negative here is close to the partial positive, which is what is called a London dispersion force. So there is an induced dipole. So that is how the London dispersion forces come about. So we've said that we have basically three types of intermolecular forces. And we've said we have the hydrogen bonding, and we've said the hydrogen bonding exists between molecules with hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen atoms. And these hydrogen bonds are the strongest of the intermolecular forces. Now, we also have dipole-dipole forces, and they arise because there exists a dipole in the molecules. So the molecules with net dipoles, so they are intermediate in terms of strength. Now the London dispersion forces, all covalent molecules possess London dispersion forces, and the London dispersion forces are the weakest kind of intermolecular forces. So we already saw the gases, and that this is the end of this part, the solids and the liquids.